So this is quiz 17, and it almost exclusively deals with the Bohr model. I didn't put in this Schrodinger model on there because we were going to do more of that today. Anyway, now, in essence, you want to remember just some few factoids about the Bohr model. The Bohr model, as we said 2 or 3 times, is the concentric ring model. Okay, and he took the postulates of Rutherford and added to them. Well, Rutherford proposed a nucleus, which was still true, positive, but Bohr and his associates proposed a concentric ring and visualized the electrons orbiting the nucleus much like the planets orbit the sun, and they live in a given orbital or they're not. Okay, some factoids is, one, there are only 7 known rings. There used to be K, L, M, N, O, P, and Q, and these refer to certain lines of a bright line spectrum. Today they're referred to in the quantum model as energy levels and have n values, 1, 2, 3, 4, and so forth. Like that. Well, there's one little, I may not have put, I know I didn't tell you about this, but one thing that was discovered in the concentric ring model is the maximum number of electrons that can be in a given orbital. Max number electrons equal 2n squared. I know I didn't tell you that last time, but I may have told you back at the beginning of the semester. Sometimes I do, because it's such a simple, when we talk about building the atom and periodic chart, just substitute the number of the orbital energy level in here. So this would hold 2 electrons max, and 2 to the 2 is 4, 8 in that level, and so 2 to 9 is 18 would go into that one, and so forth. 32 and 50 can go into that one. 3672 would go into that one. 49 49 twice, 96. Okay, getting out of my piece here, but anyway, this is a real simple little formula. Please keep that in mind, and it doesn't mean that this ring has all those electrons in it. It has room for that amount of electrons. Okay. Okay, let's see what else. Okay, it's based upon electron transitions, and these electron transitions give what they call bright line spectra. When they move from a high level to a low level, they give off energy, and this energy is seen in, if it ends on n equal 2, it is visible. Electron transitions, this bright line spectrum. So like I say, this is some factoids I'm trying to get you to learn for the exam. Okay, yeah, it might be worth talking about if we have a nucleus and the transitions, here's n equal 1, n equal 2, n equal 3, and so forth. If the transitions end on n equal 2, this is a visible spectrum. If the transitions end on n equal 3, this is infrared or IR spectrum. Right there, if they jump out to 7 and drop down to 3, you can't see the infrared and you can't see the UV. If they end on n equal 1 from wherever they're coming from, this is the UV, ultraviolet spectrum. Now they can be observed using the proper equipment and identified, so forth and so on. The analysis had 5 equations that I gave you, and you will have one of each. There's 3 of them right there. Equations for Bohr model. Actually, you have 6 if you throw in the 2n squared. So the first one was C equals frequency times the wavelength, and then I had delta E is equal to Planck's constant times the frequency, and then if we combine these two simultaneously, we could get an equation hc over lambda. Now these are what we call wave variable equations, and so when you see the red light, you can get the wavelength and plug it into these formulas and calculate certain parameters. But what Bohr and his group did is derive equations independent of this to prove that their idea of electron transitions is correct, and these were the Rydberg equations. Actually, this Rydberg came up with equations, but he applied them to Bohr model. The energy equation is delta E equals A onto 1 over n squared minus 1 over n squared, and put the initial position and final position like that. Now remember, this thing is also, while it's showing this hc over, A, this weird looking thing right here, delta E is still delta E in this context also. So you can set this equation equal to hc over lambda, and some problems come to you with that, with the wavelength, and ask you to get an energy in this context, or they'll tell you it's just a transition, a wave transition. And then you got the wave equation. In other words, you want to calculate what the wavelength based on transitions are, and that's 1 over lambda is equal to R on RH, 1 over n squared initial minus 1 over n squared final, like that. And A and R will be on your reference sheet. As a matter of fact, the reference sheet I gave you this morning, you can scurry around in that and you'll find it if you look on it. A is, I have to look it up sometimes myself. I think 2.18 times 10 to the minus 18th of a joule, I think. And R value is 109,678 reciprocal centimeters. I mean, you don't have to memorize that. The only reason I know them because I've been writing them down for 30 years, so there's nothing magical about that. But anyway, you can look those up and plug them in. You will have at least one problem on each of these, okay? And wait till they deliver the data in that capacity. Okay, so those are some of the factoids that I want you to certainly be aware of in the Bohr model. You have 3 wave variables, okay? You have speed, which will all in light, it's all the same. 3 times 10 to the 8 meters per second all the time in vacuum. Okay, you have frequency. Now I use F, or you could use a Greek nu, a little V right there, and that's per seconds. Okay, wavelength. His symbol is lambda, and it's given in nanometers, meters, or whatever. Okay, be able to convert from nanometers to meters, and so you can apply to the other equations. And energy, finally energy. Okay, electromagnetic energy. Now, light, while it's electromagnetic waves, is also referred to as photons. Light photons. Okay, that means a given color, say red waves, have a lambda 656 nanometers, and a delta E of red is equal to 3.03 times 10 to the minus 19 joules. That's a photon energy. Red light. So when we talk about some of the atomic concepts, you'll hear people talk about, well, the energy that's given off from a 2 to 3 transition is X photons. Okay, and it has an energy of such and such, such and such. Just terminology, but it is referred to in that capacity. Okay, having said all that, the acronym for color is ROY, G, B, I, V. Okay, red, orange, yellow, green, blue, indigo, and violet. Okay, so what can we say about the all the speeds are all the same. All right, frequency, wavelength, and energy. Okay, so let's talk about wavelength first. All right, when we talk about the red end is long, and then on the violet end is short wavelengths. Okay, so they decrease as you go from red to violet. Frequency, this is very slow, low, slow frequencies, not much energy, and these are fast vibrations on this end. And then energy values, this is a low energy end of the spectrum when you get down here on the red end, and it's a high energy on the violet end. So you're increasing energy from left to right, you're going frequencies going faster from left to right, and the wavelengths are getting shorter from left to right. So this is certainly a very, very important little chart, and several questions will depend on you working with the high energy, low energy, or say green in the middle, and so forth like that. Well, anyway, using all these variables, the color with the highest electromagnetic force is blue, and that was D choice in our collection. Okay. Photon of red light has a wavelength equals 656 nanometers. What is this energy given H to 6.63 times 10 to the minus 34 joule seconds, and speed of light 3 times 10 to the 8th meters per second? Well, if we've given H and C and wavelength, we'll use that last equation on there. Delta E equals HC over lambda, and this will be 6.63 times 10 to the 34 joule seconds. That 3 times 10 to the 8 meters per second. Okay, and you've got 656 nanometers. Now I told you the other day you can take 656 and just which is equal to 656 times 10 to the minus 9th of a meter, and then if you move the decimal 2 places to the left, you put it in standard form, 6.56 times 10 to the minus 7th of a meter, and that's used quite frequently in the calculations that you're looking at. So we need to enter the 6.56 times 10 to the minus 7th of a meter, and so everything will drop out except joules, and that's an energy term. So you know you've got the right combination, at least for the numbers. And red light, 3.03 times 10 to the minus 19th of a joule is the outcome. A choice in that collection. So everybody good on that? Okay. All right, number 4. Rutherford certainly postulated atoms, mostly space. We talked about that. Contains solid indivisible nucleus surrounded by electron cloud. Yes, the nucleus comprises over 99.9% of the atomic mass. So all of those are postulates of the Rutherford model. D choice. Okay, and finally, what's the wavelength of a photon of electromagnetic energy having a frequency? Okay, you're given a frequency 3 times 10 to the 8 cycles per second, or hertz. All right, and has a speed c equals 3 times 10 to the 8 meters per second. Okay, what's the wavelength? Well, if you're given c and f of the equation number 1, c equals frequency times the wavelength, and solve for wavelength, and that's c over the frequency, and the wavelength will be in meters. When you calculate it this way, 3 times 10 to the 8 meters per second divided by 3 times 10 to the 8 per second, and that's a 1 meter long wave. Okay, electromagnetic radiation, and so that is alpha on that. There, D. Okay, I will be sure to read it from that.